Hello Year 12. By now you have all received feedback on your initial attempt at the first half of your coursework. This is of course a very unusual situation in that normally you wouldn't be writing this lump of your coursework until you'd already collected your data. The reasoning behind that being that your methodology and indeed your theory could well be influenced by what you find once you've collected all of your data. But present world circumstances dictate that we cannot wait. And so I thought it was useful that I went through a couple of common errors that I saw in a lot of your courseworks and how to remedy those. And then I talked through what I'm going to be asking you to do next over the Easter holidays, which effectively is writing the full first half of your coursework. In order to do that, I need to talk through a context that lets me talk about a number of things. And I thought the easiest way to do that is when I'm demonstrating how to present errors, how to present your essay in general, how to explain your control variables, how to set out your results tables, where necessary I'll use the context of a GCSE required practical. And the required practical I will use is how does the weight applied to a spring affect its extension. Now this is just Hooke's law, but it puts us on a nice level playing field where I can now talk about an experiment that you know. That is, just take a spring, add a weight to it, record its extension, add another weight to it, record its extension again, and keep doing until you get a nice little graph of your weight against your extension, which will have gradient k, f equals k, x. If you didn't have that zero intercept, then probably you hadn't worked out extension but total length. And that would be something that is well worth talking about in an evaluation, for example. So firstly, we'll talk about presenting errors. There were lots of situations here where either you were talking through a methodology and you weren't talking about your errors each time. So for example, in this experiment, you may well have said the spring was 15 centimetres long. But actually you would need to say the spring was 15 plus or minus 1 centimetre long. Or let's say that your resolution actually was 0.1 centimetres, that would be 15.0 plus or minus 0.1 centimetres. So your error should always be to one significant figure. That only changes if you measure 10,000 or more data points, and that will never be the case here. So you round your error to one significant figure, and then you match the decimal places of your value to the decimal places of that error. So let's imagine instead we're measuring our extension, and we have our instrumental uncertainty, of 0.05 centimetres, and I record an extension of 20 centimetres. I would quote that as 20.00 plus or minus 0.05 centimetres. Note I put brackets around my whole value and then my units outside of those brackets. It's vitally important in order to get communication marks that you're doing that accurately. Second is a very simple one. Please delete my scaffolds. All of those words that I've put into the base document saying things like control variables, you should have at least 5 of these. Method, written in a paragraph in the past tense reporting style. Get rid of all of those now. You've had that information. You've used that to inform your initial writing. You don't need it there anymore. Third, explaining control variables. Control variables are arguably the most important part of your whole methodology. I would expect that at minimum they're going to take half a page. For most of you, they'll be closer to a page. Each control variable should have its own individual paragraph, and it should have what the control variable is, why changing it has an impact, and that needs to be specific and explained using physics, and then what you do to control it. So in this experiment, for example, one control variable would be the temperature of the spring. This is because changing the temperature of the spring changes the spring constant. This is because the particles in the spring are vibrating with different average kinetic energies at different temperatures, therefore the intermolecular forces between them are different, and therefore the restoring forces enacted by those intermolecular forces are different. In order to control this, after taking your data, wait 10 minutes before taking another data set. So you see that very clear structure there. What is the control variable? Why does it matter? And what is the effect of it happening? You should probably also add in there, incidentally, increasing temperature will make the restoring force lower, and then you would have to reference that to be really clear. And then finally, what are you doing to control that variable? That doesn't have to be perfect. You could just be trying to limit the overall impact. In my case, waiting 10 minutes won't guarantee it's at exactly the same temperature, but it will mitigate the effect of heating effects from placing a mass on that spring. So it is vitally important you talk through that. Finally, I saw a lot of issues with setting out tables. It's probably worth just doing this in Word, and even if you're writing in LaTeX, you may just wish to screenshot and insert as an image. You can code in LaTeX at any table you want, but it is harder, so it's up to you. So for this experiment, my independent variable always goes on the left, so I have my weight, and I have my units in brackets, and then I have my instrumental uncertainty below that, so that may be plus or minus 0.1 newtons, and I need my units there twice. And let's say I'm going to take weights of 0, 1, 2, and 3. Well, I'll lose a mark here because my error is to 1 dp, and I've quoted my values to 0 dp. So it's to be 0.0, 1.0, 2.0, and 3.0. And I'm going to be measuring my extension. Now, I might want to record length and then extension as a subsequent column. If I wanted to, that would be fine. In centimetres, let's stick with our instrumental uncertainty, 0.05 centimetres. I'm going to repeat my data. Let's say I do it 3 times and then take an average. So I have my headings, but I also now have my columns for each data point and then my average. And I'll just take one of these as an example because you obviously want me to fill this in yet. But let's say I measured 21.2, 18.6, and then 19.4. All of those would come with an issue because my error is to 2 dp. So 21.20, 18.60, 19.40. Then I could take my average and work out my estimated random error from half the range. But at this stage, I don't need to do that. So that's how we set out tables. Independent variable, dependent variable, and any repeats and averages all in the same table. If you're doing more than one experiment, let's say, for example, I were using 3 different springs here, or I were changing the temperature of the spring to 3 different values, then I would have 3 different tables. Spring 1 and then spring 2 would be the same table, but for the second spring, and spring 3 would have its own third table. So they're the common errors that I found that I wanted to talk through. But it's also worth now talking about what I'm going to ask you to do next. Now, we'll give more guidance on this in the task that I post on Monday, to be due in 2 weeks from the date it is set. That is when you would go back to school, where school's open. I'm going to be asking for a full introduction now. So obviously you're tidying up all of the things I've commented on. So you've got your real-world context, which I've given you information on. You've written a full methodology, which I've also commented on, and then a blank results table. But now I'm going to look for a full introduction. In all of your IAs, you have a comment on your document that says full introduction should include. And what it should include is all of the relevant theory, both mathematical and qualitative, that will get you to a hypothesis that will hopefully be mathematical in itself, that you can then use to analyse your data. So once you've finished that introduction, you should not be introducing any new physics or indeed any new mathematics after that point. And I've given you a rough structure for that, but in general just work from simple to complicated. So in this situation, you would begin with just why a string stretches when a weight is placed on it. Then you would talk about Hooke's law. You may well derive Hooke's law, and then you would come up with your hypothesis that included details of the graph you would draw and how you would find your spring constant. And your hypothesis would be that you expect the extension and the weight to be directly proportional to one another. So that'll be your full introduction. And I'm then going to mark this second one on some of the assessment criteria that will be used in the real thing. So I'm going to mark this firstly on personal engagement, and that's out of 2 marks. Now you get personal engagement in a number of ways. Firstly, you can get it by doing anything impressive. Typically that would be deriving some of your theory, showing you really understood what was happening. But I also assess personal engagement through discussion of a preliminary experiment. You can't do that at the moment, but you would use it to check that your range and interval are appropriate, and perhaps to refine your methodology. And I also check it, crucially, on your control variables in your methodology. Is there enough detail that shows you really thought about the experiment? Are you actually showing an awareness of the different factors that could affect your data? So that's personal engagement out of 2. I can also give you a mark for exploration out of 6. Now that is your introduction, your theory, your real-world context, and also your methodology. So it's basically everything I'm asking you to write, except for the blank results table. And to get 5 marks, that's what you should be aiming for there. I rarely give a 6. To get 5 marks there, you need to have all relevant theory. Ideally, it will be mathematical. Most of it will be derived. You need to show a good understanding, not just that you're regurgitating a textbook. Then your methodology should be valid, clear, and detailed. Effectively, I should be very happy with everything that you're writing, and I shouldn't see any real gaps in what you've written. The final criterion I can mark you on is communication. Communication is out of 4. And it is quite important. Everyone should be getting 4 on this from the very beginning. One thing that's very common is for you not to proofread your work. You will lose marks if it's full of typos. You will lose marks if you're not communicating clearly, coherently, and also concisely. You also lose marks in communication if your errors are not reported correctly, or if you miss out errors entirely. And you would also lose marks in your communication if when you state an equation, you don't define the variables and we've not met them before. So communication really is how well does it read? And remember that the audience that you're writing for is one of your peers. So you could do an awful lot worse than get together with someone in the class or in any physics class that you're friends with and agree to read one another's work and just give suggestions for, I don't understand what you're saying here, this isn't clear here, you need to reference this, you need to discuss this a bit more, this doesn't make sense, this is contradictory. So I hope that this video is in some way helpful to giving you a good guide as to what you need to fix and also what you need to go on to do. I will remain contactable throughout the Easter holidays, both on this page and via email, so feel free to bombard me with questions because it is literally what I am paid to do. Good luck.